Hello students, this is Professor Chalai, and in this video we're going to look at acid-base titrations. As always, you can follow along with our Chapter 4 workbook. By the end of this video, you should be able to perform acid-base titration calculations. Now, at this point in our class, all of you have already performed an acid-base titration experiment in lab and have done some acid-base titration calculations. So if you think you have a good handle on the experimental side of acid-base titrations, you can skip forward to the calculation part of this video. But let's look at an acid-base titration in a little bit more detail. And here we're going to look at our acid-base reaction where we're going to use HCl as our acid. So if you remember from an experimental setup, we have our HCl in our Erlenmeyer flask, and we've added an indicator in there. And then we've had our base in our burette that we added dropwise. So I'm just using HCl as our acid and NaOH as our base. And the equation for their reaction is HCl and NaOH reacts to form a salt and water. This is an acid-base reaction. So let's think about what's happening as we add NaOH from our burette into our Erlenmeyer flask when you open the valve. So in the beginning, in our flask here, we only have HCl and indicator and other stuff, but HCl is pretty much what we have. So because we have HCl in there, it's an acid, the overall solution would be acidic. Then we add a little bit of NaOH slowly from the burette, and that little bit of NaOH that we add immediately, almost immediately, reacts with some HCl to form some salt and some water molecules. And this keeps happening. We add NaOH, that NaOH then reacts, so it gets used up with a little bit of the HCl to form more products, more NaCl and more H2O. At this point, the overall solution is still acidic, right? Because we still have some HCl in there. The other components in there are NaCl and water, which are not really acidic or basic. So our overall solution is still acidic. But then there'll come a point in time where we've added enough NaOH to such that it reacts with all of the HCl to form NaCl and water, and there are no more HCl or NaOH left over, and so the overall solution is neutral, right? And that is our equivalence point. Our equivalence point is when the amount of acid and base exactly react with each other, or exactly neutralize each other. There we go. So here our pH has, well, we haven't talked about pH yet, but our solution is neither acidic nor basic. Then as we continue to pour more NaOH from our burette, right, there's nothing for it to react with, and so it starts to pile up, and now our solution becomes basic. And so to be able to tell exactly when that equivalence point is reached, we use an indicator. So an indicator is just a dye that has different colors in an acidic and basic solutions. So that way you could be able to tell when the solution is transformed from an acidic solution to a basic solution, and so you're able to stop the burette from adding any more NaOH. And that's the principle of an acid-base titration. In class, we use a phenolphthalein indicator that actually changes color around a pH of 8 or so. But again, we haven't talked about pH, and you won't until Chem 160. So that's the principle behind an acid-base reaction. You start with an acidic solution, you slowly add base until it neutralizes, and then if you keep adding base, it becomes a basic solution. Okay, so the equivalence point then is when the moles of the base and the moles of the acid completely neutralize each other. All right. I know you've had some practice performing acid-base titration calculations, so I would like you to try numbers 29, 30, and 31 on your own first, and then I'll go over the calculations with you. So I'd like you to pause the video right here and try them, and then unpause when you think you have the answers. Okay, so let's look at number 29. We're performing a titration calculation. We start with 20 mils of H2SO4, sulfuric acid, and it has an unknown concentration. Okay. On the other side, we have 22.87 mils of potassium hydroxide, and its concentration is 0.158 molar solution. Our first step is to write a balanced molecular equation, and this is very important because we need to know the mole ratios of acids and bases. In the example that I give here for HCl and NaOH, we see that we needed 1 mole of HCl for 1 mole of NaOH to completely sort of react with each other. But this is not always going to be the case. So we always need to find a balanced chemical equation first. So let's figure out what it is. We have H2SO4, it's going to be aqueous, reacting with KOH, that's our base. So plus KOH, aqueous, to form some salt and water. The salt is going to be potassium sulfate. Potassium has a charge of +1, sulfate has a charge of 2-, so the formula should be K2SO4. And if we look at our solubility chart, if we remembered, the formula is K2SO4. It's aqueous. And then, like all acid-base reactions, we'll have water. So this is the salt, and we'll form water, liquid. Okay, let's try to balance this equation. We have, let's look at the K. There's 1 K on the left, 2 on the right, so we'll make that a 2. That gives us 2 OH, which means that the 2 OH minus here and the 2 H plus over here will give us 2 water molecules. And that should make everything balanced. So in this equation, we see that 1 mole of acid, 1 mole of H2SO4 rather, should react with 2 moles of KOH. Okay. Now we need to find the unknown concentration of H2SO4. This is simply a stoichiometric calculations where we know the volume of H2SO4 and we need to find the concentration, and we know the volume and concentration of KOH. So if you look back all the way back when we first started talking about stoichiometric calculations, I showed you this chart where you can convert from any component, any value from one substance to another value of another substance just using the balanced chemical equation and mole ratios. So in this example, we know the volume and concentration of the KOH, which means we can find the moles of KOH. Using the mole ratios, we can find the number of moles of H2SO4, and using the volume of H2SO4, we can find the molarity of H2SO4. Really, stoichiometry, you can follow this flow chart to find any component when you're performing stoichiometric calculations if you can't figure out what to do. So let's go back to where we are. So let's do that. So we start with our volume of KOH. So let's write let's write that. We start with 22.87 milliliter. We need to use the concentration, molarity, to convert the number of moles. But molarity is moles per liter, so we first need to convert this volume to liters. There we go. Now that we have that, we can use the molarity to convert the number of moles of KOH. And I'm just going to add, let me just do it this way, mils of KOH. And we know that 1,000 mils is 1 liter, so mils cancel out. And we know that the concentration is 0.158 moles of KOH per liter of KOH. So we have liters cancel out, KOH cancel out, and we're left with moles of KOH. Okay. Now, from our balanced chemical equation, we see that 2 moles of KOH reacts with 1 mole of H2SO4. So let's write that. 2 moles of KOH, to cancel out up here, reacts with 1 mole of H2SO4. And now that we know the moles of H2SO4, we can find the concentration by using the volume, dividing by the volume. So the volume was 20 mils, so divided by 20.0 mils of H2SO4. However, whoops, I shouldn't have canceled that. However, concentration is moles over liters, so we need to convert the milliliters to liters. Let's use orange. So we know that 1000 milliliter is 1 liter. And so we have moles of H2SO4 divided by liters of H2SO4. So we plug all of this into a calculator and we should get 0.0903 molars of H2SO4. So let's look at the steps again. We start with the volume and the concentration. We start with the thing that we know. We start with the substance that we know, which is the KOH. We know the volume and the concentration, so we start with that. We use the volume, convert it to liters, and the concentration to find the moles of KOH. We use the mole ratio to convert moles of KOH to moles of H2SO4. Once we know the moles of H2SO4, we divide by the volume in liters to get the concentration. 3 sig figs. Okay, let's look at number 30. If you haven't done so yet, please pause the video and complete it now. So here it's asking for the volume of NaOH that has 0.200 molars. And it tells us that we titrated 35.00 mils of 0.140 molars HBr. All of these stoichiometric reactions, as we need to start, for all of these stoichiometric reactions, we need to start with a balanced chemical equation because otherwise we won't know the ratios that the molecules are reacting with. So let's do that. NaOH, aqueous, plus HBr, this is our acid, hydrobromic acid, aqueous, gives us Na and Br, or ions, so NaBr, sodium bromide. It's going to be aqueous if you look at our solubility charts. And H and OH gives us H2O liquid. That's our acid-base reaction. Let's balance this. 1 Na, 1 Na, we're balanced there. 1 OH and 1 H plus gives us 1 H2O, that's balanced. And 1 Br minus, 1 Br minus, we're all balanced. So yes, we didn't have to do anything here, but we should at least write down our equations just to make sure that they're balanced. All right, so here we have the concentration of NaOH, but not the volume. Whereas for HBr, we have the concentration and the volume, so that is our known quantity, so that's what we're going to start with. So let's do that. We start with 35.00 mils of HBr. As always, we need to convert mils to liters if we're going to use molarity, so 1000 mil is 1 liter. And then the concentration, to convert it to number of moles, is going to be 0.140 moles of HBr per liter of HBr. So all that cancels out. Now that we have moles of HBr, we need to use our mole ratios. And our mole ratio says that 1 mole of HBr, hydrobromic acid, reacts with 1 mole of NaOH. I know that 1 divided by 1 is just multiplying by 1, and some people might want to skip this step, but it's always good to write it such that our units cancel out, and we know that we're actually converting from one compound to another in our equation. Okay, now that we have moles of NaOH, we need to find a volume. They give us the concentration. So if they give you the concentration, which is moles over liter, and they're asking you to find the volume, then you need to divide by the concentration. So we divide by 0.200 moles of NaOH over liters of NaOH. Right? Remember, molarity is moles over liter. So moles of NaOH cancel out, and we're left with liters of NaOH in our answer. However, they want their answers in milliliter, so we just need to convert liters to milliliter. Let's do that. 1 liter, so that cancels out, is 1000 milliliter. So we're left with milliliters of NaOH in our answer. So milliliters of NaOH. And you plug all of this into your calculator, and you should get, if I did all of my math right, 24.5 milliliters. The steps are all the same. We start with the thing that we know. In this case, it's HBr. We know the volume and the concentration, so we can find number of moles. We use the mole ratio to convert from HBr to NaOH. We divide by the molarity to find the volume, and we convert it to milliliters because that's what the question was asking for. Finally, let's look at 31. Again, if you haven't done this, please pause the video, do that first, and then come back. They already give us the balanced chemical equation, so we're good there. And for our phosphoric acid, they give us the volume, but not the concentration, so that's our unknown. And then for NaOH, they give us the concentration, and they give us the volume. So let's start with NaOH. We start with the volume, 26.38 mils of NaOH. Let's convert that to liters. So 1,000 mils is 1 liter. Let's use our molarity to convert that to number of moles. So 0.100 moles of NaOH per liter of NaOH. There we go. Let's cancel out all these guys. Okay, now we have moles of NaOH. We need to do mole ratios, right? In this balanced equation, 3 moles of NaOH reacts with 1 mole of H3S phosphoric acid. So let's do that. 3 moles of NaOH reacts with 1 mole of H3PO4. There we go. And then we have moles of phosphoric acid. We need to find a concentration, which is moles over liter, or moles divided by volume. The volume is 30 mils, so let's divide by the volume. Divided by 30 mils of H3PO4. But concentration is moles over liters, not milliliters. So let's do that final conversion, 1,000 milliliter over 1 liter. So milliliters cancel there. And we end up with this whole long line of stuff that if you just punch all of this into your calculator, you get 0.0293, right? 3 sig figs, moles over liter, which is just big M, molarity of H3PO4. And that's it. That's your answer. If you have any questions about any of these, please let me know, but I'll see you in the next video. Bye.